So this is just a short discussion on the material in section 7.2, which is the last unit of the course. And there's actually kind of a lot of material in here. And so I'm not going to expect you to know, like put a lot of difficult problems from on the final on this. So and I'll let you know more about what has to be on what you need to prepare for the final. You definitely should know about the natural, and some of this you probably know, e to the f of x equal the exponential function e to the x. And you know about the natural logarithm function. The ln of x is just a logarithm with base e. And I'm sure you did that at some point if you don't remember. Okay, so here's this kind of a theoretical basis for this. So let's say we define this function to be the area curve. Let's just look at the area from 1 to x under the curve 1 over t. Okay, so E is the area. So E is the number where the area from 1, like in this shaded region right here, it's already shaded. I'll shade it in some more. So how far do we have to look under this shaded region for the area to be 1? How far do we have to go to the right from 1? And that number we're going to call E, right? So E is the number. So when we substitute, so what number do we have to substitute into this equation here, into that formula for that integral to be 1? That number is E, and it turns out to be a very important number. And it's about 2.7 something or other, but it just goes on and on and on. And then we know that from the fundamental theorem of calculus, we know that the derivative of f of x is just 1 over x. The derivative of that area function is just 1 over x. So we're going to call, so basically this is a new thing that we're doing here. We're taking this integral here, which is just the area. It's just this area function, the area under the curve 1 over t from 1 to x. And we're going to call that function ln of x. And it turns out that's actually it behaves like a logarithm where the base is e, and you can actually prove that. And from the fundamental theorem of calculus, you take the derivative of the area function and you just get 1 over x. And so the domain is, okay, so the domain is from 0 to, so we'll say the domain is from 0 to infinity. And then the range, and so we'll just actually, because you can't cross that line. You can't cross the asymptote x equal to 0. Yeah, so the domain is 0 comma infinity, and it goes on and on in either direction. If x becomes infinite, the area becomes infinite, and you can make x much smaller than 1, and then you actually get negative area, right? So here the area is just negative for x less than 1. Okay, so and the area, and so it can be, so if you as you get closer and closer to the area to 0, as x gets closer and closer to 0, the area becomes negative infinity. And you can, we're not going to prove it, but the function's continuous. And then again, so if f is the area function, the area under the function, 1 over t, then the derivative is just, 1 over x. And then you can take the derivative again, use the, just use the power rule, and you get minus 1 over x squared. Oh, so the derivative, the second derivative is always negative, which means the second derivative is negative, so the curve is always concave down. So this is the graph. Basically, this is the shape of the graph of any log function. So at 1, it goes through at 0. Okay, so and you can actually prove that this area function, right? You can actually prove that this area function, that's easy to prove, I guess. I'm not saying it's hard to prove, but it's not, to me, necessarily obvious. Behaves like a log, right? Behaves like a logarithm. That the area of from a times b. Let's say you go you start at 1 and you go to a times b units. That's equal to the area going a units to the right of 0, plus the area going b units to the right of 0. And the same thing is true for the area of a divided by b. It's the area going a units past 0 minus the area going b units past 0. And I don't think that's so obvious, but that's how a logarithm behaves. So this function here has all the properties of a logarithm. Okay, so so now let's just use these properties. Again, this is just reviewing properties of logarithms, which you probably had in your last algebra, your most advanced algebra course. And so like how can we expand natural log? So first of all, we know that natural log of E is, by definition, is 1. That's the area that we go out. How far, how many units do we go to the right of 0 so that the area under the curve from 1 to x is 1? And that number is E. So we know that the natural log of E, right? So that's just 1 here. That's this property right here. And so let's just expand this. So we'll just use that product rule. So we're using this rule right here, the natural log of a times b. That's true for any logarithm. It's the log of e to the 4th plus log of square root of 3x plus 2. We're going to try to reduce this as much as possible. So we're going to use the power rule, right? So then we also use this rule 5 to bring down the exponent. So logarithms turn, first of all, logarithms turn multiplication into addition, right? And logarithms turn exponentiation into multiplication, right? So we're taking e to the 4th and making it 4 times log of e, which just turns out to be 4 because log of e is 1. And the log of the square root of 3x plus 2, well, that's 3x plus 2, the 1/2. So that's 1/2 log of 3x plus 2. And I'm sure you did exercises like that at some point in your math career. Okay, so let's go the other way around. Now we can actually simplify this, like log of x minus 3 times log of y. So, well, 3 times log of y is log of y cubed. So log of x minus log of y cubed is x over y, log of x over y cubed. And then subtract log of 2 from it. Once again, we use division. You know, log of x divided by y cubed minus log of 2 is log of x divided by y cubed, the whole thing divided by 2. And then you simplify, you get log of x with a 2y cubed as the denominator. Okay, so so we know that the derivative of the log function, the log of x is just the area, is the area function. And so the derivative of log of x is just, by the fundamental theorem of calculus, is 1 over u du. And if we actually want to include negative numbers in there, so we'd have to go log of the absolute value of x. But we'll just say the derivative is 1 over u. Okay, so now let's just find the derivative of each function here. So okay, so we have to use the chain rule. So the derivative of the log function is the log of 3x plus 1. So it's 1 over 3x plus 1. And then you take the derivative of 3x plus 1 and you get multiplied by 3. Okay, now what about the derivative of y equals x to the 5th times log of x? So you just use the product rule, right? X to the 5th times the derivative of log of x is 1 over x. And then it's a log of x times the derivative of x to the 5th, which is 5x to the 4th. I think this is kind of a reasonable problem maybe for the exam. It's not using some advanced properties of log. I mean, because it's a lot coming at the end. So I'm trying not to make it too hard, but I think this is kind of a reasonable problem. Now, what about the derivative of log of 5, the expression 5t over t minus 4 squared? Now you can actually use the chain rule. You can go 1 over 5t t minus 4 squared and then take the derivative of all of this. But simplify it first. Use the division and the exponentiation properties, and we get g of t is 5t, log of 5t plus log of t minus 2 times t minus 4. And now just take the derivative. Take the derivative. So you don't have to use the chain rule. So yeah, so the log of 5 is a constant, so its derivative is 0. Log of t is just 1 over t. The log of t is the derivative, that is 1 over t. And the derivative of t minus log t minus 4 is 2 over t minus 4. Here's another one which I don't think is so unreasonable if we use the chain rule. So again, the derivative of log of x is 1 over x. So now let's just use the chain rule. It's 1 over sine of x. The derivative, and then use the chain rule. The derivative of sine of x is cosine of x. So you get the derivative of the log of sinus. Oh, I'm sorry, I kind of skipped a step. The original function is log of sine squared of x. Again, we could just use the chain rule on sine squared of x. But again, let's just simplify. Again, so the log function turns exponentiation into multiplication. So take that 2 out of multiply. Now take their derivative. It's a lot easier. You don't have to take the derivative of sine of x squared now. So, but you could just take, you could take the derivative. You can go 1 over sine squared of x. But now you have to take the derivative of sine squared of x, which isn't really that hard either. It's 2 sine of x cosine of x, and you get the same answer. Okay. See, times cosine of x. So, and then you could cancel one of the cosine of x, and you end up with the same answer, 2 cosine of x over sine of x. But if you use the rules of the logarithm to simplify and then take the derivative, I just think it just makes your life a lot easier. And maybe my life too. Okay. And here's another one. So when you take the derivative, like log of the absolute value of cosine of x, just pretend the absolute value isn't there. So it's 1 over cosine of x, and then the derivative of cosine is minus sine. So you get minus tangent of x. So here's kind of an interesting problem. We want the tangent line to the function log of x over x, where x is e. So now if you actually, now f of e is just 1 over e, right? F of e is log of e. Well, log of e is 1 all over e, so that's 1 over e. Okay, so the function goes through the point e comma 1 over e, and now you find the derivative, okay, and you have to use, now we'll just use the division rule, right? So you take the log of x times the denominator, which is x times 1 over x, and then log of x times the derivative of the denominator, which is 1, and so you get 1 minus log of x over x squared, and then you just plug in, well, then when you, so it turns out f prime of x is 1 minus log of x over x squared, but so f prime of e just turns out to be 0, 1 minus natural log of e over x squared. Well, the natural log of e is 1, so that's 0. Okay, so it's a little bit, okay, it's kind of a whirlwind definition. Okay, so now we know that the derivative of the natural log is 1 over x. So the integral of 1 over u. So this is a really big thing. This is something you really need to know for your next course. The derivative of 1 over u du is the natural log of u, the absolute value of u plus c. And we're putting the absolute value there in case the u is a negative number here. So let's just look at this kind of like 7 here. So some of it is stuff that we've, the only thing there that's new here is that 5 over x. Okay, and so we don't know how to take the derivative, because when the 1 over x to the negative 1, you can't use the power rule on, because you add 1 to the exponent and then divide by, so you add 1 to the exponent, negative 1 plus 1, you get 0, and then you can't divide by 0. So okay, so we've been waiting till we got to this natural log. Okay, so most of that's just stuff we've known before, but the integral of 5 minus 5 over x is minus 5 natural log of x. So definitely this formula here is really critical right here. So here it turns out to be, okay, so the integral of dx over 4x minus 1. Well, you can use the substitution. It's not necessarily so obvious. Let u equal 4x minus 1. So 1/4 du equals dx. So that turns into 1/4 the integral of 1 over u du. So you get 1/4 natural log of u plus c, and then go back to the original variable. This is kind of a reasonable problem, I think, here. Okay, so now it starts maybe getting a little bit harder. 9. What you can see here is that the numerator is the derivative of the denominator, or a multiple of the derivative of the denominator. Okay, so that's what we have in 9 here. The numerator is you take the derivative of the denominator, you get a multiple of the derivative of you get the multiple of the numerator. So the derivative, so let u equal t squared plus 5. Let me say this again. So you let u equal, this is the denominator. Now when you take the derivative, you're getting a multiple of the numerator. So when the derivative of the denominator is a multiple of the numerator, the log function is going to be involved. And it takes a little practice to see that, but that's kind of one of these, I'm sure you'll do more of this in Calc 2. Here you just have to use, you see, the numerator is a constant, and you see something like to the first power. We'll use a substitution, it's probably going to be log. So this number 11 improper fraction, so I'm not going to put that on the test. I think there might be some in this on MyLab. You just have to use, polynomial division. So when the numerator is a higher degree than the denominator, you have to use polynomial division. But yeah, this is not going to be on your test, but it might be on MyLab. I doubt I even put this on the quiz. Like I said, I'm not gonna, yeah, so, okay, but I'll probably just put real basic stuff on the quiz too. Yeah, so what happens is you use polynomial division, and this turns into x plus 2 plus a negative 1 over x plus 1. Again, this is when the degree of the numerator is greater than the degree of the denominator. You have to just use polynomial division and reduce it. And then you'll probably end up with one of the functions, the integral part of that being the log, being the antiderivative being a log. So here's another one, which I think is kind of, again, I'm pretty sure you'll review this again in Calc 2, the integral of the tangent. Well, again, this is the case where the derivative of the denominator is equal to the numerator, or a multiple of the numerator, right? The derivative of cosine of x is, well, it's minus sine of x. So the derivative of the denominator is equal to a multiple of the numerator. That's when you know that the log comes in. But again, I'm not going to put something like this on the test. Okay, here. So, here's another one. I'm sure I keep saying I'm sure you're going to learn this in Calc. I have taught Calc 2 many times, but not in a while. And I have to assume they're going to review this, but I'll be honest, I haven't taught it in a while. Okay, so now the secant function, it's not so obvious. God, see how some clever person just realized, well, you multiply secant of x just by 1 in the form of secant of x plus tangent of x divided by secant of x plus tangent of x. Oh, look at that. The derivative of the denominator, which is secant of x plus tangent of x, you take the derivative of that, you get the numerator, right? So it just turns out, so you just rewrite secant of x in this form, secant squared of x plus secant of x tangent of x in the numerator, secant of x plus tangent of x in the denominator. You let u equal the denominator, which is secant of x plus tangent of x. You use substitution, and you end up with 1 over u du. You get log of u, and then you just substitute back in secant of x plus tangent of x. Again, this is not, like the notes say here, memorize this. So I'm not going to ask you these kind of, like the integral of tangent or these functions here. I mean, the trig functions you need to know, integral over cosine and sine, not these other ones. And now we can actually then do these, now that we know how to do the integral of cotangent, we can do these definite integrals. So, and I'm not going to go into this because it's not going to be on your test. Okay, so then again, here's another one, like an integral of, I think this is maybe too hard right now for our test because it's coming so quickly at the end of the year. But how would you log cubed of x times the integral of the antiderivative of log of x over x? Okay, so well, first of all, you can use the you could actually, well, no, I take that back. So it's log cubed, it's not log of x cubed, be careful, okay? So, but yeah, what you have to recognize, when you take the derivative of log of x, you get dx over x. So you either recognize that or you don't. I mean, you recognize that by doing a lot of problems, right? So in this kind of problem here, you have log of x in the numerator, and then you have dx over x, over x. You let u equal log of x, and then you get the differential is dx over x. So, okay, so then just a couple more things here. So the inverse of the log is the exponential function, right? Because the log of x, the area function, also we can prove that it basically behaves like a logarithm where the base is e. Okay, so its inverse is e to the x. Okay, so okay here, and so yeah, so e to the x and log of x are inverses of each other, and so you can actually. So one thing, this is something you may have seen in again, this is algebra. How do you, let's say, solve 35 equals 4 e to the 2x? Well, just divide each side by 4, so you get 35 over 4 e to the 2x, and this takes natural log of each side, and then just solve for x. And when you take natural log of e to the 2x, natural log of e to the 2x, that's 2x times natural log of e, but natural log of e is just 1, so that's 2x. So you can solve for x. And you probably have done this at some point in your algebra course. Like here, natural, you want x is in the logarithm, just raise both sides, to the e power. So e times natural log of 3x plus 1, well, they're inverses of each other. So what it is, you get 3x plus 1 is equal to, basically that's what this means, right? This is, log base e equals 2. It means e squared is equal to 3x plus 1. That's basically the definition of a logarithm. And now solve for x. And you probably learned that in your intermediate algebra courses. And here you can actually prove, it's kind of a remarkable property that, and this is something that's important, the derivative of e to the x is also just e to the x. And I think it's the only function that has the property. The derivative of the function is the function itself. So that's the kind of thing we want to know for the final. And then now you can just use the chain rule to find the derivatives. Like the derivative of e to the minus 3x, well, it's e to the 3x, e to the minus 3x, and you take the derivative of the inside part, which is minus 3x, and you get negative 3. So here's another one where you have to do harder one. Example C there, t cubed times e to the 3t squared. But again, you just use the product rule and the chain rule. And then since the derivative of e to the x is e to the x, the integral of e to the x is e to the x. So like here, what's the integral of 1 over x plus e to the x? Well, it's natural log of x plus e to the x plus c. Here's kind of a harder one. You have to recognize, well, the derivative of 1 over x is dx over x squared. And you can use substitution. You equal 1 over x. I definitely would review this kind of stuff before calc. You'll probably have an opportunity in calc too, but I think these integrals are a little bit hard for the final. But like these derivatives, I think are reasonable. Like right here, what's the derivative of log of x squared plus 1? Well, y equals 1 over 5 plus 3x. That's just from the earlier part in the course. But if you take the well, I think this derivative is reasonable, and taking the derivative of 4e to the 3x is reasonable, and the integral of 5e to the 3x is reasonable. Okay, so then here also just the chain rule. We know that the derivative of log of x is 1 over x, so just use the chain rule. It's 1 over x squared plus 1, and then the derivative of x squared plus 1 is 2x. So I think these are reasonable derivatives. Just use the chain rule. And here, yeah, this would be, so yeah, that's a reasonable problem. Just let u equal 3 to the x and then use substitution. And I think I'll just stop sharing there. And so I'll write the quiz, and after the quiz, I'll just put which problems you should review. So it'll probably be like a few kind of, I think, problems that shouldn't take too long to solve from this section. But definitely, we want to know that the derivative of log of x is 1 over x, and that the integral of e to the x is e to the x. That's something that you really need to know for Calc 2. Knowing the properties of the log function that we did at the beginning of this discussion, like the log of a times b is the log of a plus the log of b, really very important. But we only have a brief time to talk about this, which is too bad. Okay.